Hey guys, welcome back for another video of our LeetCode 75 study plan series. Today we are in the binary tree depth first search category. We are going to be doing this problem called leaves similar trees. And our instructions are: consider all the leaves of a binary tree from left to right order. The values of those leaves form a leaf value sequence. For example, in the given tree above, the leaf value sequence is 6, 7, 4, 9, 8. Two binary trees are considered leaf similar if their leaf value sequence is the same. Return true if and only if the two given trees with head nodes root 1 and root 2 are leaf similar. So in this case, it's true because we have 6, 7, 4, 9, 8, 6, 7, 4, 9, 8. Even though these trees aren't exactly the same, they have similar leaf similar values. Oh my gosh. This is pretty straightforward. Basically, what we're trying to do is perform a depth first search on the bottom leaves of our binary tree, and if they are the same, then we're going to return true. As we can see in this method right here, we have a Boolean return type. So we're just going to be evaluating if the two values end up being the same. So the first thing that we're going to want to do is, if we're going to be comparing two values or two lists of values, we're going to be needing to make a list for each root, for each tree node, right? So what we're going to start out with is a list of integers, which are going to represent the values of these nodes, and we can call this leaves 1 to represent root 1, and let's just initialize this. So new array list. All right, and then let's do the same for the second root node. All right. And then now what we were going to want to do is to just kind of make this a little bit more readable. Let's make a helper function that performs our depth first search. You'll see that this is common with a lot of DFS problems. You'll just make a helper function which you can call in your main method, or leaf similar method in this case. So basically we'll just create a private static method, and it'll just be a void return type, and we can just call this DFS. And basically what we want to pass in is our root node, right? So we can just do tree node root, or let's just call it node. That's more appropriate because it's not always going to be the root node. And then let's do a list of integers, and we'll call this leaves. Alright, so let's go ahead and create this method real quick, and then we can call it in our leaf similar method. So basically what we want to check first is if the node that we're passing in is null. So let's go ahead, because if it's null, then obviously we can't do anything with it. So if our node is not null, alright, now we're going to want to check another thing. We need to basically, what we're trying to check for is if it is the bottom, right? If there's no more left or right values. So in order to check, we have to see if there's any more values. So basically what we want to do is, if node dot left is equal to null and node dot right is equal to null, then that's when we want to add the value to our list, right? Because we're going to call this for each root node, we're going to call the depth first search method. So then we're going to add that value to the list if it's one of the bottoms, and this is how we can tell if it's on the bottom. All right, so we're going to do leaves add node.val, right? We're not adding the node itself, we're adding the integer value that the node holds. Okay. Now, after we get out of this, so say it's not the bottom node, and we need to keep going further down to see if it's to finally come to our final node. So in order to do that, we need to use recursion. So what that means is that we just have to call our depth first search function again inside of the depth first search function. So we need to do that for the left and the right side. So we'll do node.left, and then we'll pass in the leaves list, right? And then we'll do node.right and pass in the leaves list. All right, so that's all we need for right now. Okay, so let's go back to our leaf similar method. Now what we need to do is we need to call the DFS method, and we need to pass in our root values. So root1 and then leaves1. All right, so now we have our list that's going to have all of the bottom node values for our first root node, the first one that we're comparing, right? And then we do the same thing for the second binary tree that we're comparing to the first. Okay, so then now at this point, after calling these, we have these full of our bottom values for each tree. So since this is a Boolean return type, we're going to make an expression to determine whether or not it's true and then return that Boolean value. So what we need to do is do return leaves dot equals leaves2. All right. I forgot to add a 1 right there. Leaves1 dot equals leaves2. All right, and then you might be thinking, wait, why don't we use the equal here, I'll type it in the comments. Why don't we do leaves1 equals leaves2? And the reason that we don't do that is because the double equal sign checks for pass by reference, or it checks the reference value, right? So it checks if it's the same place in the memory. Equals checks the value. So it checks if they have the same values, not their place in memory. So it wouldn't be appropriate to use leaves1 equals leaves2. It would actually give us an error, so we can't do that. So that's why I use the dot equals method to compare the two. All right, so let's go ahead and run. So I made a quick typo. I just put root1 again right here, so we're going to do root2, and then we're going to go ahead and run this again. Awesome. All right, so we got accepted for our first two test cases. Let's go ahead and submit this, and we are good. All right. All right, so let's analyze the time and the space complexity. So for the time complexity, we're going to have big O of n, and technically it's actually big O of n plus m, where n represents the nodes in root 1 and m represents the nodes in root 2. So there's two things that take up the time complexity, right? So the first thing is the depth first search, right? We're going through all the leaf nodes, which can be represented by k. K can be up to size n or m, depending on if it's root 1 or root 2, if the tree is lopsided. So worst case would be big O of n, and then best case is big O of k, and k represents the number of leaves in the binary tree. And then also, when we're comparing the two lists at the end, that takes a time complexity of big O of k, worst case big O of n. So for those of you who thought that might be a little bit confusing in my wording for it, to make things simple, it's just considered big O of n time complexity. And then for the space complexity, it's going to be kind of the same as the time complexity. Best case, big O of k, representing the number of the bottom tree leaf values. And then the worst case is big O of n. So we're going to call it big O of n space complexity. Because remember that we're using recursion, and recursion adds to the stack, right? During runtime. So we can add up to n nodes if the tree is to be lopsided. In most cases, it's going to just be k, representing the leaves once again. So I hope that you found this video helpful and insightful, and maybe it helped you to learn more about depth-first search. I certainly hope that it did. Please go ahead and like this video if you found it helpful, and then subscribe for more related content. We still have more problems in this category, so specifically if you're looking to kind of master lists and depth-first search, this is going to be great for you to subscribe to. And we will see you in the next video. Thank you.